Most people picture an Antidetect browser as one of two things, either Chrome with a proxy box bolted on the side, or some magic cloak that turns you invisible. It is neither, and the gap between those two fantasies is where all the real understanding lives. What actually happens under the hood, in the code that answers a website's questions about your machine, is what decides whether your profiles hold together or quietly leak. Today I want to open the box and walk through how these browsers are really built, because there are only two ways to do it, and that single architectural choice explains most of the quality difference between the tool that holds up and the one that gets your accounts linked. Quick note on where this comes from before I start. I run real proxy and cloud phone farms, and I test these browsers hands on the way multi-accounters actually use them. I am going to keep this educational and defensive, how the tools are engineered, not the recipe against any particular platform. And there are no undetectable promises anywhere in this, because understanding the mechanism helps you judge which tool is honestly built. It does not make anything invisible, unbannable, or risk-free. Knowing how the engine works just stops you paying premium money for a script sitting on top of stock Chrome. Start with the thing these browsers are built to control, the fingerprint. When you load a page, a site can quietly read dozens of signals from your browser: the canvas drawing, the web renderer, the installed fonts, the screen size, the time zone, the user agent, and a long list of smaller details. On their own, each one is ordinary, but combined, they form an AD specific enough to recognize the same machine again on a different account. The whole purpose of an Antidetect browser is to present a different, internally coherent set of those signals for every profile you run, so the profiles do not all trace back to one real device. Here is the core split, and it is the one idea to take from this whole video. There are only two engineering approaches to changing those signals, and every tool on the market is really one or the other underneath its branding. The first approach patches the browser itself, shipping a custom build of Chromium or Firefox with the spoofing baked into the source code. The second approach leaves stock Chrome completely alone and injects JavaScript on top to rewrite the answers as they are requested. Same goal, two utterly different mechanisms, and the difference decides how well the disguise actually holds. Take the injection approach first, because it is the simpler one to picture. The tool runs normal Chrome, and just before a page's own scripts execute, it slips in a piece of JavaScript that overrides the functions a website uses to read your machine. So when the page calls the function that reads the canvas, or the one that lists your fonts, or the one that reports your screen size, it does not get the real answer from the hardware. It gets the faked answer the injected code hands back. It is cheap to build. It rides on top of a browser you already trust to render pages, and for a quick demo, it looks like it works. The problem is what that override looks like from the other side, and this is the tell that sinks lazy injection tools. When you replace a native browser function with your own JavaScript, the replacement stops looking native. A website can ask a function to describe itself, it can walk the chain of objects the function came from, it can even trigger an error and read the stack trace, and the function that was quietly rewritten by hand gives itself away in all of those. So a thin injection tool often gets caught, not by the value it returns, which might be perfectly plausible, but by the plain fact that the thing returning it was clearly tampered with. The disguise leaks at the seam, not in the costume. Injection has a second weakness that is just as stubborn, and it is about consistency. Browsers usually expose the same underlying fact through more than one path, several different APIs that all end up reporting your screen, or your language, or your hardware. An injection tool has to intercept every one of those paths and make them all lie in exactly the same way. Miss a single path, and the real value leaks through a side door while the front door shows the fake, and now the two disagree. A detector does not even need the tampering tell. It just notices that the same machine gave two different answers to the same question, which no real machine does. Now the other approach, the patched engine, which is what the serious tools are really selling. Instead of sitting on top of stock Chrome, they compile their own build of Chromium or Firefox, and they change the value deep inside the code that actually generates it. The number that describes your screen, or the pixels that make up the canvas, is altered at the layer that produces it, long before any website script gets to ask. So when the page reads it, the answer is native the whole way down, because it genuinely came from the browser's own machinery. There is no JavaScript override perched on top for a detector to find, because nothing was added on top at all. That is why a properly patched engine feels so much more solid than an injection layer, and the reason is structural, not marketing. Because the change lives inside the engine. The same faked value flows out of every AP path automatically. So the multiple paths agree with each other by default instead of needing to be patched one by one. And the function still looks completely native, because it is native, just compiled to return a different result. That single design decision erases the whole category of problems that dog injection, the rewritten function that betrays itself, and the one path somebody forgot to cover. It is more coherent, because coherence is built in rather than bolted on. None of that comes free, and the cost is the reason not everyone does it. Maintaining your own fork of Chromium is a serious, ongoing engineering job. Chrome ships a new version every few weeks, and every time it does, the team has to pull those changes into their fork and rebuild the whole thing, over and over, forever. If they fall behind, your profiles start advertising an old Chrome version that almost nobody in the real world is still running, and that stoutness becomes its own quiet fingerprint. So a patched engine is only ever as good as the team keeping it current, which is exactly why an abandoned tool at any price is more dangerous than it looks. It is worth seeing how a single profile is actually stored under all of this, because that is the other half of the machinery. Each profile is really its own sealed container, holding its own cookies, its own local storage, its own cache, along with the fingerprint values and the proxy assigned to it. Those containers are walled off from each other, so that nothing, no cookie, no cached file, no leftover login, ever bleeds from one profile into another. When you open a profile, the tool launches the browser engine pointed at that specific container with that profile's spoof values loaded, which is what lets one machine run many identities that genuinely do not know about each other. The proxy fits into that same launch, and mechanically it matters that the two are bound together. When the tool starts a profile, it wires the assigned proxy into that browser instance, so every request from it exits through that address. And the well-built tools go further, setting the profile's time zone and locale from the proxy's location and routing DNS and word tech through it too. So the network story matches the device story. The point is that the browser and the proxy are not two separate things you happen to use together. They are launched as one bound unit per profile, and the tool that makes that binding sloppy is leaving a gap where the two halves can drift apart. There is one more structural choice worth naming, which is where all of this actually runs. Some tools do everything on your own machine and keep the profile containers on your disk, while others hold the containers, and sometimes even the browser itself, on the vendor's servers and stream the result to you. It is the same spoofing engine either way. The only thing that changes is where the data physically lives and who is holding it. That is a real decision about custody and about how easily a team can share profiles, but do not let anyone sell you cloud or local as inherently safer for the fingerprint itself, because the coherence of the disguise comes from the engine, not from the address of the disk. Mobile emulation is where the two approaches separate most sharply, so it is the best stress test of how a tool is built. Faking a convincing phone is far harder than faking a desktop, because a real phone differs from a laptop deep below the user agent string in its touch support, its screen characteristics, its reported memory, and the whole graphics stack underneath. A tool doing it properly changes those deep signals inside the engine, so the profile is a phone all the way down. A tool faking it only rewrites the user agent text, which leaves a desktop machine wearing a phone's name tag, while every deeper signal still screams laptop. The mechanism is exactly why a mobile checkbox on a pricing page tells you almost nothing on its own. So what does all of this mean when you are actually choosing a tool and you cannot see its source code? You may not be able to read the engine, but you can absolutely read the result, and the mechanism tells you precisely what to look for. Open a profile and do not just confirm that the values changed. Check whether the functions returning them still look native, and whether every AP that reports the same fact agrees with the others across several reloads. A tool built on a genuine engine patch passes that quietly, while a thin injection layer trips somewhere, on the tempering tail, or on two paths that disagree. That test is the practical payoff of understanding how the box works inside. And then the honest ceiling, because this is where knowing the mechanism keeps you sober. Even a perfectly engineered engine only ever controls the device half of your identity. It does nothing about the quality of the proxy you attach, nothing about how you behave once you are logged in, and nothing about the history your accounts carry. A beautifully patched browser on a filthy proxy, or driven carelessly, still gets flagged, and no architecture changes that. Understanding how these tools work stops you overpaying for marketing and stops you trusting stock Chrome in a costume. But it does not and cannot make anything undetectable, because nothing does. So under the hood, an anti-detect browser is one of two things: a patched engine that changes the signals natively so the disguise is coherent all the way down, or a JavaScript layer that rewrites the answers on top of stock Chrome and leaks at the seams. That one architectural choice drives most of the difference between a tool that holds up and one that quietly links your accounts. Which tools ship a real, well-maintained engine, and which are thin injection wrappers dressed up in bold promises, is exactly what I test hands-on, with the proxies attached, and the full written reviews and the picks I actually trust are all at antidetectreview.org, with no undetectable promises anywhere. If this made the inside of the box make sense, subscribe for more honest, tested anti-detect browser reviews, and I will see you in the next one.